This morning, and this one is entitled Frontiers in the Laboratory. One of the most impressive things about Steve is that he seems to know almost everything. And is this on? Maybe not, doesn't matter. And I've known that he's done laboratory work in addition to atomic physics and astrophysics and astronomy and so on. I'd never realized he had a connection to gravitational wave detection, but maybe we'll find out what that is now. Our next speaker is Professor Jason Hogan, who's here at Stanford, and he's going to tell us about a new approach to gravitational wave detection.
Great. Well, it's great to be here in honor of Steve Kahn. It's my pleasure to tell you a little bit about some ideas we have. My background is in atomic physics, and this is an idea we've been really excited about for a while now, and it's an attempt to approach gravitational wave detection using some of the techniques of the rapidly evolving field of precision measurement in atomic systems. And so I want to try to express what I think can be an interesting alternative to detecting gravitational waves. First of all, if I want to just express my enthusiasm for why gravitational wave astronomy I think is so exciting, and I think it is going to be exciting in the future. So gravitational waves, these ripples in space-time that can propagate across the universe and teach us about some of the most extreme and violent systems that we know about in astrophysics. And so you can imagine a binary in-spiral of compact objects. I think the artist's rendition here showing perhaps two black holes spiraling around, emitting gravitational radiation. And as they do that, the orbit decays, and eventually you can get a coalescence, and then you can study that gravitational wave source to learn about this violent destruction of these two bodies. And so, what's maybe one way to think about the excitement is we know every time we open up a new frequency range in the electromagnetic spectrum, we learn new things. There's always more to see. And so in some sense, gravitational waves are a whole new carrier. They're a whole new frequency band, and they can tell us things about sources that are otherwise maybe difficult to see using electromagnetic radiation, of course, because these are sourced by different kinds of stuff. Instead of oscillating electric charges, we have waves that can be generated by the motion of mass or mass energy. And so it's sort of new sources that might not emit a lot of light, could still be strong emitters of gravitational waves. Of course, the other thing that you can do is if you can look at these waveforms, as I alluded to, you're learning something about strong field gravity. You can see, you can essentially test our understanding of general relativity and whether or not it agrees with the waveforms that we can detect of such systems. And finally, and maybe even more exciting, is the possibility of maybe doing cosmology with gravitational waves. Of course, the idea that you could look back even further in time than you can with light is very exciting, and to look back towards the inflationary era. And so we think that there's a possibility of that too, and it's worth pushing. So this is the sort of lay of the land in terms of the kinds of detectors, certainly not an exhaustive, but kind of the big two out there in my mind. So on the ground, we've got a number of large-scale laser interferometer detectors similar to LIGO, Virgo, GEO, and others on the horizon. And what these detectors are generally laid out as is a Michelson interferometer configuration, where if a gravitational wave comes in, as shown here, you can get a displacement of the end mirrors in each of the arms of the interferometer. And it turns out that these detectors are best for frequencies of waves above about 10 hertz, up to about a kilohertz or so. And if you want to go lower in frequency, it turns out it's better to go into space. And that's primarily because the Earth is a noisy thing, and to get away from vibrational noise, seismic noise, gravity gradient noise, you need to get off of the Earth. And so this is a picture of the LISA concept, which is targeted sort of for the millihertz band, where there's a lot of really exciting sources. And you can sort of see that here in this chart that I borrowed. So this is kind of the gravitational wave spectrum in terms of sources that we might expect. So you can see starting at sort of the audio band and these higher frequencies, tens of hertz or so, is where the terrestrial detectors live. And then below that, you've got the space detectors, which can see this blue band of sources. So those are consisting of some of these black hole mergers and other sources listed here. And so I guess the one thing that I wanted to point out is some of the sources that you would expect to see in a terrestrial detector are also visible in the lower frequency range in a detector such as LISA. But the thing that's really exciting about that band is that in that range they tend to live for a lot longer, and that's because if you imagine how long a source that's emitting gravitational waves at 10 or 100 hertz is, it's clearly near the end of its life and about to be destroyed, and so you only get really a burst event for those types of sources. But that same merger that shows up in the LIGO band probably was present in the lower frequency millihertz band, and there you can actually look at the orbits for maybe months or years and get a better sense of what this inspiral is doing. And at lower frequencies, we've got things like pulsar timing array. Of course, we've heard a lot about cosmic microwave background polarization in the last year or so, and so I think each of these is really exciting, of course, and where I want to try to point for this atom-based approach that I'll be telling you about is sort of in this LISA band and also in a frequency range sort of between the two, where there's a little bit of a gap, as I'll show you. But before going any further, I wanted to give maybe a higher level picture. Why is it worth even talking about using atomic physics techniques, or why is an atom an interesting way to detect gravitational waves? And basically, the atom, we like to say, is a great inertial test particle, a great gravitational test particle, since it's neutral. So if you think about the types of non-gravitational forces that can impact the atom's motion, those are going to be reduced because the atom doesn't really interact very strongly with those forces. So they follow the geodesic really well, which is what you want. And then what's really interesting to us is that we have this really great tool, which I'm going to tell you about, atom interferometry, which gives us a way to essentially characterize the geodesics, measure where these atoms are as a function of time, and that is of course a critical point for measuring variations caused by a gravitational wave passing by. And then a final and a bit more subtle point, which I think from the point of view of building a detector ultimately is really interesting to me, is that you can talk about doing a so-called single baseline detector with an atom-based approach. So of course the LISA triangle requires 3 satellites, 3 spacecraft, and the reason for that is actually it's interesting. So if you think about LIGO, for example, you've got 2-arm design. And the reason for that is fundamentally technical in some sense. If you wanted to, you could. If I go back maybe a slide or two, in principle, the effect of the gravitational wave, sort of cartoonishly shown here, would be if you had a couple of test masses with some separation, that distance will oscillate. So in principle, in one dimension, you're already getting the effect of a gravitational wave. And so the question is, why does LIGO need 2 sets of arms to look for gravitational waves? In principle, the 2 test masses on one arm of LIGO is enough. But in practice, it's a technical problem with the laser. The noise, the frequency instability of the laser makes it not possible to detect at the level of noise that you need the distance between those 2 mirrors. And so the trick is to send that noisy laser simultaneously down 2 different arms. So that way, whatever noise you have on the laser is going to be common to the 2 arms, and since the gravitational wave is a quadrupolar distortion, you can get a factor of 2 enhancement in the signal when you subtract the 2 arms, but more importantly, the noise cancels. And so that's the sort of fundamentally why this Michelson geometry is great. And LISA has to have 3 different arms, or really at least 2, for the same reason. It's because the noise that on this laser light that's being beamed between the test masses in LISA, you need a way to cancel that as a common mode, and so you send the noise down 2 different directions and you can cancel it out. And so what I hope to show you is that with an atom approach, we can get around that constraint and have only a single baseline, which of course could lead to a pretty big reduction in the complexity of the system if you only have 2 satellites instead of 3. Okay, so let me now maybe give a quick intro to the technique atom interferometry that we use to measure accelerations and other inertial forces on atoms to motivate what we can do in such a detector. So you know about laser interferometry, where you have light incident on a beam splitter. You send that light along 2 directions, and using a couple of mirrors, you can bring the light back together. With a second beam splitter, you can combine the 2 beams and get an interference pattern. You can see that here, spatially, for example. Or if you were to look with 2 photodetectors, of course, you can see fringes in the sense that light either shows up in one port or the other, depending on the relative phase between the 2 paths. In the same way, we can build an interferometer using atom de Broglie waves, using matter waves. And so this is sort of a cartoon of that. You have this solid black line starting off here on the bottom left, represents the trajectory of an atom. And we can split that atom using an atom beam splitter, shown as this wiggly line, so that part of the atom follows the upper trajectory and part of the atom follows the lower trajectory in this picture. And so by bringing those 2 paths back together and using a final beam splitter in a similar way, we can get an atom interference pattern. And you can see this is some data that we took of a de Broglie wave interference pattern, where these regions of blue and red correspond to regions of constructive and destructive interference of the matter wave. And by reading out this fringe pattern, or by analogy, for the 2 ports for the light interferometer, we have 2 little ports down here, this red and black line, kind of closely spaced. But by counting the number of atoms in each of those 2 ports, we can infer something about the phase shift in this interferometer, which in this case corresponds to the acceleration that the atom felt during the sequence. So this is a way of building this particular geometry with 3 pulses, is a way to build an atom accelerometer. So a bit more detail on that, how we actually implement these beam splitters and mirrors for atom de Broglie waves. At least on Earth, we always have a nice vacuum tube shown as this tube here in cross section, and we have an atom cloud shown as this blue dot, which is in free fall in the vacuum tube. And then we use pulses of laser light shown with these red arrows here along the vertical axis to implement the splitting and recombining of the atom de Broglie waves. So you can see the same cartoon again, the height of the atom versus time in this case. So the atom is following its free fall trajectory until we apply a beam splitter at time t0, which what it does is it puts the atom in a quantum superposition of 2 states. One is the initial state the atom had with whatever velocity that is, shown as this black line, but also half of the atom is in the superposition of having absorbed a photon. So this dashed line corresponds to the fraction of the atom's wave function that received a kick from the momentum associated with that photon that it absorbs. So with that relative velocity between the 2 arms, you can get a spatial separation between the 2 halves of the atom as a function of time. And that's what opens up this interferometer. And so just to give you a sense, if you then stop the experiment in the middle here, you say take a picture of this state where I've got half of the atom here and half of the atom here, you see this picture. This is an image we took in the middle of one of our interferometers. And you clearly see 2 bumps here, which correspond to the probability amplitude of finding an atom in either this lower location or this upper location, point B or point C. And so at that point, you're in this quantum superposition of 2 different locations. Now, if we take that picture, of course, we collapse the wave function. We don't get to measure anything on that shot. So usually we don't do it. We don't do that. We in fact bring them back together with a mirror pulse in the middle and produce interference at the end, as I described before. And then we can measure the acceleration that the atom felt by looking at that fringe pattern. So to make this thing as sensitive as possible for gravitational wave detection, it turns out we want the time to be long, and we want the separation to be big. That basically opens up a very large area, which is good for sensitivity. So our hardware looks sort of like this. This is what we have at in the Varian Physics building at Stanford. There's a 10-meter scale vacuum tube, as I mentioned, where the atoms are in free fall. The 10 meters gives us a couple of seconds to watch the atoms. They start off at the bottom of this system. There's an atom source that produces Bose-Einstein condensates. Atoms of around 3 nanokelvin in temperature are produced and then launched in a ballistic trajectory into a region where we can perform this atom interferometry while they're falling. What we get is something like this. So this is what the data looks like. Once again, the interferometer showing the position of the atom versus time, with this trajectory representing the fact that we open the interferometer into an upper and a lower path. And then if we look at the interference pattern here, you can see I've got the blue line corresponds to one of the ports, and the red dashed line corresponds to the other port, just like in an optical interferometer. But here you see a CCD image that we took of the atom cloud. And so now we see atoms either in the upper port or the lower port, and that's how we read out the interference pattern, which you can see going on here. So as a function of the phase shift, the phase difference between the two arms, the atom population swings. It oscillates between being in the upper location or the lower location. And so this is the signature of destructive and constructive interference as a function of the phase difference. And so just basically by counting atoms in each of those two locations, we measure the phase shift. And as I mentioned, that tells us about acceleration. So for this particular interferometer, in that 10-meter tower, we're dropping the atoms, or excuse me, the duration of the interferometer lasts for over 2 seconds. And that ends up giving you acceleration sensitivity of 7 × 10⁻12 g in each shot. So it takes 2.5 seconds to go up and down. And at the end of that, you've measured, you know something about g to that precision. So that's why this is exciting. That's a very, very precise, a very high precision accelerometer, and can we use that to look for small wiggles from gravitational waves? So this would be how you could adapt this idea to a gravitational wave detector. Basically, you need two of these separated by some large baseline. So you can see it's kind of got the cartoon of our atomic fountain, like the one I showed you, this 10-meter tower, one say up here and one say down there. And so what that means is that each of these has a cloud of atoms. Each of those is an accelerometer in the way I described. And so by comparing the two, we basically can look at the difference in acceleration between those 2 points in space. And if a gravitational wave comes by and is stretching the vertical axis, then that will show up as a differential acceleration. Now, one of the critical things, of course, is noise. How do you get around all the other things in the world that could cause the differential acceleration? And so one of the big ones, as I mentioned in the case of LIGO and LISA, is laser noise. The fact that the laser is noisy will affect your ability to measure the distance that you're interested in. Now, the critical thing here is that if we align these two interferometers along a line like this, we can use a single laser beam to manipulate both of the atoms at each of the locations. So the atom here and the atom there are manipulated using the same laser pulse, and so whatever noise is on that laser is common to the two interferometers and cancels when you look at the difference in acceleration. So that's really that's the reason why we can get away with doing just one linear dimension for this detector. Now it turns out that the frequency that these sensors are good at seeing is roughly around the time that you drop the atom, so a couple of seconds on Earth, unless you make a really tall tower. And so for a terrestrial detector, we're talking about like Hertz level frequencies, or maybe a fraction of a Hertz. And so once again, to go into sort of the millihertz band where LISA is, that's going to require a space detector, so we don't have to make a tower that's too tall. And so that might look something like this. So you can see maybe an artist's rendition here of two spacecraft with this red line between them, the laser that's interrogating the atoms, these two little white figures representing the atom clouds, which may be inside the satellite or outside the satellite. That's something that we can consider doing either. And you can basically imagine sending this common laser between these two satellites and implementing atom interferometry on each end of a long baseline. And so the kind of sensitivity that you can get is shown here in this strain sensitivity curve. So the strength of the gravitational wave on this axis versus frequency down here. And for reference, you can see in blue, this is the LISA strain sensitivity curve. So of course, the lower the better. If you look at LIGO in the audio band, they have a much lower frequency, much smaller sensitivity at higher frequency. And LISA's down here in the millihertz. And the red line is the sensitivity that we could potentially do with the sensor I just described in the previous slide. So a couple things to note, that this, for sort of equivalent or nearly the same range that LISA can do, the atom sensor could be much smaller. So in particular, for the parameters here, it's 1,000 times shorter than the LISA baseline, and yet we're still sort of able to get into that same sort of sensitivity range. And that's, and I'll come to why that is in a moment. You can also see in this blue square where we think that a terrestrial detector could go. As I mentioned, it's set by the fall time, so that's going to be around 1 hertz probably for a terrestrial detector. And it's kind of an interesting range because you've got LIGO sort of not going much below 10 hertz, and then LISA also stops somewhere around there too. So there's a bit of a gap sort of in the tenth of a hertz range where a lot of interesting sources do live. You can see some source curves shown here. These sort of blue and green lines. As I mentioned, a lot of the sources that make it into LIGO's band when they sort of coalesce originally came from lower frequencies, of course, when they were earlier in their life. As these source curves sort of indicate, the detectability of those tends to go up as you go to lower frequencies, and that's in some sense because you can look at them longer. They survive for many orbits. And so some of the LIGO sources would show up in this terrestrial band that we think we could detect in the sort of sub-hertz range. Okay, so I wanted to talk a little bit about a couple of, I think, exciting new results that we have. Perfect. A couple of exciting new results that we've got in developing the technology. There's certainly some things that need to get done to make this a reality. And one of the big ones, as I mentioned, is the wave packet separation. The reason we can get this sensor 1,000 times shorter than the LISA sensor in the previous sensitivity curve that I showed you is because we can get what we call like a phase enhancement technique. The bigger we can split the atom, the more precision that we get on measuring the acceleration, and so that allows us to compress the baseline. The handle that we have on that is that instead of using just one laser pulse, we can use a series of laser pulses to accelerate one arm away from the other. As you can see here, this upper arm gets kicked multiple times by this series of this pulse train, and that really brings one arm away from the other. And so that lets us get sort of centimeter scale separation, as this picture shows. But what we'd really like to do is push that as much as we can. Can we go to tens of centimeters or maybe even a meter scale separation? That would really give an increase in sensitivity. And so this is sort of our most recent data. We've been working on this the last month or so and trying to basically add more pulses to split the atom by as much as we can. And so for a 2-second long interferometer, we were able to apply 20 photons worth of momentum difference, and you can see the two wave packets shown here separated by 12 centimeters. So this is then, if we bring it back together, we can get interference, which is shown here. You can see the two ports with the constructive and destructive interference between these two shots. And so this interferometer works and represents an increase of about a factor of 10 in sensitivity from the data that I showed you originally. And so I just wanted to take a quick minute just to point out that I think this is already kind of interesting from an atomic physics point of view, or at least I get excited about it, that you've got an atom that's really in two places at once separated by a macroscopic distance. And so, of course, we all know about Schrodinger's cat, and that you can, that our intuition is challenged by the idea, okay, certainly we understand quantum mechanics makes sense, or we have a lot of experience with it with the microscopic scales, but does it really work when we go to things like the size of a cat? Can a cat be in two places at once? Well, this isn't a cat, this is just a cloud of atoms, but what I can say is it's big enough that I can fit a cat between those two atoms now, or at least a small cat. So it's really getting to be macroscopic. Just wanted to touch on two other developments we've had in the last, or fairly recently. So I mentioned we're using smaller baselines, but what if you could use larger baselines? Why don't we use LISA-like baselines, use our phase enhancement to do even better? We've had a technical constraint on that in the past, which is that since we need these lasers to be shared by the atoms, the beam has to be collimated. And that sets a constraint on how big your telescope is. You can't go to a very long baseline without requiring ridiculously large telescopes. Even though we're talking about sort of 10 to the 3 kilometer baselines, LISA is using 10 to the 6 kilometer. And so is there a way to do that? And so we have a refined technique that we've been thinking about in the last half a year or so where we can actually do LISA-like baselines now and get away from this constraint that we had on requiring collimated lasers. And basically, it uses a technique very analogous to the laser links that are used in LISA, where the laser beams that are sent between the satellites are allowed to diverge, so that received light is very low in intensity. And the idea is you can simply you can do a phase lock to a local laser that has enough intensity to interrogate the atoms. This laser you can see here is it's sort of act like an amplifier for the incoming light that can then manipulate those atoms. And so this technique lets us do LISA-like baselines then with the same sort of phase noise cancellation along a single baseline that we think is so interesting. And so this is kind of just a design study of that. You can see this green curve. With the longer baselines, you can get to this dashed line, the LISA curve, with very conservative atom parameters. This is 2 photons of splitting between the 2 halves of the atom, which is the very first data set I showed you, and you can see that extra baseline lets you get pretty much similar sensitivity. Of course, if you can do the kind of phase enhancement techniques, these multiple photon splittings that I showed you, this is a 12 h bar K curve. You can do maybe a factor of 10 better than LISA with that. In fact, I showed you data of 20 h bar K splitting, and so that's already twice as big as this essentially. So, anyways, this is a new tool we think for optimizing the design. I wanted to say a word about stochastic sensitivity. So from the point of view of cosmology, one way to talk about it is your ability to resolve omega GW, the energy density of gravitational waves, fractional energy density. And so you can see there's a number of sort of exciting cosmological sources on here, including inflation, shown in this blue area. And so you can see LISA in black and these 2 curves I just showed you from that previous slide coming in here. It's interesting that this curve can dip into the inflation band here, but it's worth, of course, noting this gray band here is the so-called white dwarf binary confusion noise, which would probably limit the science reach of that. But there are targets out here where we think those foregrounds are not present, and you could potentially do sort of at the 1 hertz frequency range, perhaps build a detector that was capable of seeing inflation. So we're looking into that as well as for a future detector. And then the last thing, in my last couple of minutes, I just wanted to say that there's another experimental result we had. To make these detectors work, you need really cold atoms, like the coldest atoms that have ever been produced in the picokelvin range. And so we developed we worked with a technique called atom lens cooling to do that, where essentially, in the same way as if you take a diverging beam of light, this is a set of laser beams, say, it's diverging, you can use a lens to collimate that laser beam. You can do the same thing with a diverging cloud of atoms, and that's what we mean by temperature, of course, that the atom cloud is diverging. So we can collimate that with an atom lens, and so we did an experiment where we applied a laser pulse to act as a lens. The diverging beam of atoms can be refocused, and you can see a dramatic reduction in the width. And what that corresponds to, if we were able to show that we were able to bound temperatures at about 50 picokelvin that we produce with this technique. So we think that's as far as we know, the coldest kinetic temperatures that have ever been produced or measured. And so that's the kind of range you need to be able to do these long time, low frequency detections. And so I think with that, I want to wrap up and thank you all for your time. Thank you.
Thanks very much for a really fascinating, spectacular display of atomic physics. Questions? We have a couple of. Okay. We have time for, let's say, a couple of questions.
Could you comment on the cost of the mission compared to LISA?
No. Yeah, so I think. My take on that is that I think that's something we really want to look more into. My perspective is that there is a complexity reduction going from 3 satellites to 2, which could make an impact. The actual cost of getting satellites into orbit can be the dominant source of the budget, even if you've got it's all about mass in some sense. So it's hard to say just straight up that that's going to be cheaper. So this is not drag free. So everything that I showed you. So in particular, yeah, I didn't get a chance to talk about that. But the fact that our atoms are freely falling inside the satellite, we have dramatically less noise constraints on the satellite bus in terms of pointing and vibration noise. So we think modest enough that they don't require it could really be a generic satellite bus that doesn't require any drag-free. So that, I think, is another big complexity reduction. But I think there's a lot of controversy in this, and I don't want to just come out and say, it's going to be cheaper, because I'm not an expert in that. And I look towards the complexity reduction and maybe risk reduction as having 2 satellites instead of 3 could be a win. So I think it's worth having a conversation about that.
Okay, real quick, 2 more. This one.
You were mentioning about if you do it in space, whether the atoms are inside an enclosure or outside.
Right.
I thought the vacuum, particularly if you are around the Earth, the vacuum, and near a satellite or a spacecraft, the vacuum is kind of bad. What kind of vacuum? I mean, you presumably need like really good vacuum. Is it realistic to think of doing it outside of the window?
Yeah. So in fact, I think we think it can be done. Yes, we think it can be done outside the satellite. And I think the major limitation is the dirt of your own satellite, for sure. You need a 100-second lifetime, basically, and so you need essentially ultra-high vacuum-like conditions. And so I don't think that's ruled out. I think it would be great to keep them inside. That's a more conservative approach, obviously. And so for the last designs that I just showed you with these sort of longer baselines, that there we are, have been completely assuming that we would be inside some sort of meter scale vacuum enclosure inside a satellite. And so that's kind of, I think that's an evolving thing. But absolutely, the vacuum is good enough. At least, even sort of at 1,000-kilometer orbits, the lifetimes are good enough, except not counting your own satellite, but from the sort of background residuals of the atmosphere.
Okay, real quick in the back.
Related question: is there any coherence loss in the environment in space, either from solar wind or radiation pressure or the like?
Oh, that's great. Yeah. So we like to say that those types of perturbations cause atom deletions rather than that systematic. So basically, if a high energy particle comes in and hits one of the atoms, that atom is lost from the cloud. It reduces our signal noise ratio, but it doesn't impart. It doesn't change the acceleration that we measure. In particular, we don't have to worry about proof mass charging or things like that, because those clouds that get hit by those particles, those atom clouds, those atoms are lost. So it's a signal reduction, but not a systematic.
Jason, just to follow up on that.
Yeah.
This is something I've worried about a lot in the past. Spacecraft charging can create an electric field in the vicinity of your atom cloud, even if you ignore the individual interactions with the atoms. That has to be a perturbation, I would think.
That is a good. I think if a strong electric field would be a concern, absolutely. So the atoms are polarizable, so we are suppressed. We're not insensitive completely, but it's something that we'd have to think about for sure. Yeah. So I haven't thought much about that, but I think that's a great point. Yeah. I mean, presumably if you're inside a vacuum enclosure on the satellite, that could be.
Yeah, but the vacuum enclosure can get charged.
The vacuum enclosure could get charged, so you'd have to think about that. I agree.
So Steve has already made a contribution to gravitational wave detection. Thank you very much, Jason. So our next speaker is Bill Goldstein, who knows something about laboratories. He's the director of the Lawrence Livermore National Lab. And I don't actually know what the title of his talk is going to be, but I think we're going to find that out shortly. Frontiers in the Laboratory. Is this all set?
Well, except the computer's frozen, so other than that, I'm okay. No, that's the one that just ended. I was just mentioning to Jason, who I haven't met, that actually Livermore, we work with Mark Kasovich and AOSense as well on the same technology in a completely different application. Which I can't talk, that's right, I'm sorry. I can't. Yeah, okay. So, gee, thanks for the invitation. It's a real privilege to help honor Steve. He was, I think, at Columbia around the time as a assistant professor, maybe as around the time I was a graduate student there. So, I'm working on trying to feel like this isn't a thesis defense. But I've been asked to talk about laboratory astrophysics or astrophysics in the laboratory, and I'm going to give you sort of a survey. Maybe a very selective survey of kind of what's been going on there. And I think you'll see as I go on that this is I think it's a very appropriate topic to be included as part of this tribute. Now, laboratory astrophysics is a venerable field, I would say, that goes back quite a ways. I don't know if it's further than this, but certainly back to the early parts of the 20th century. And spectroscopic work by Ed Lane, who measured spectral lines in the laboratory, and actually those measurements helped to interpret things about the sun, and in particular the temperature of the sun. So this is quite an old field. Now, what I'm going to be focusing on actually is what I'll call high energy density astrophysics. So this is laboratory astrophysics, and strictly speaking, or roughly speaking, has to do with matter at pressures of above a megabar and temperatures above roughly 100 EV or so. I know there's a great deal of laboratory astrophysics that goes on under relevant to other conditions, but that's what I'm going to be pretty much sticking to. So strictly speaking, actually, what Ed Lane did qualifies as high energy density laboratory astrophysics, but I think actually it's fair to say that Steve made actually advanced it to a new level, and that sort of starts here. And what I'm showing here is kind of the span that I'm going to be talking about. So starting in 1988, going to 2004, actually 2015, just this month. And the paper on the left-hand side there, actually first author is Steve Kahn. It includes also a group at Livermore and also at UC Berkeley. And I think I saw Roger Falcone come in the audience. So Roger's actually one of the co-authors on this. And so if I mischaracterize it, you can, save your questions for later. The main thing this was a attempt to use lasers to measure photoabsorption under conditions relevant to astrophysical objects, in particular, I think accretion disk systems, as a way of benchmarking or preparing for the kind of X-ray measurements that would be made by the Newton and Chandra telescopes that were anticipated. I think it's fair to say that this paper did not make the evening news. But on the other hand, right next to it is a result from very recently out of the Rutherford lab, the University of Oxford, by Giancarlo Gregori's group, which, if you look there, the encomium for them, so they made the top 10, one of the top 10 breakthroughs of the year, according to Physics World. So that, of course, that's an English, a British journal. They didn't make the APS top 10. But the encomium here has to do with, I'm not sure if you can read it, lasers ignite a supernova in the laboratory. Okay, so this field has come a remarkable way, and I think it's fair to say that Steve's had a lot to do with that, and I'm going to show you that. There were false starts along the way. So when I looked for follow-ups to that original paper, 1988 paper, I actually couldn't find any. And I should have mentioned, actually, there are no actual results quoted in it. Well, it wasn't quite a Gedanken experiment, but it was close. It was the idea that, nope, that's absolutely right. Except for this one paper I found, which was kind of a follow-up to it. This appeared in a IAU colloquium. But again, here you can see, if you look at the discussion there, the last part of the paper, we've devised a method for measuring photoabsorption cross-sections of blah, 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 blah. That's simple and reliable, and we hope to do it in the future. That's what it says. Near future. Once again, I could not actually find any follow-ups to this particular paper. But I think it's worth noting that there are very few references at the end. I didn't cut them off here. So this really was at the beginning of the field. And you know, I'm joking around, but in fact, you'll see as I go through that this was this work has ended up being phenomenally successful. However, I think whatever happened here actually turned Steve off of lasers. And to this day, I believe he will not return to a laboratory astrophysics experiment using lasers, even though I've actually tried to convince him to do that. Instead, along with Lawrence Livermore, he turned to using an electron beam ion trap, a system that we had developed at the laboratory, along with, in a collaboration with Peter Beiersdorfer at Livermore, started a long-standing set of body of work that, as you can see here, started before 1990, and by a couple of years ago had led to over 70 papers on laboratory astrophysics. So a tremendously productive collaboration, and one that's made a number of important contributions in a number of fields. The original, I think, by the way, I have to thank Peter for these slides, and I think that you know, he made the point that the original motivation for this was puzzling things in the spectra, in the X-ray spectra that were being taken from ASCA, as well as to prepare for the coming X-ray observatories of the next decade and the next century. That was, as I say, very successful. So there were mysteries in the ASCA data. This is pointing to one that's significant one, actually one that's persisted persisted to this day, almost to this day anyway. This shows the X-ray emission from Capella as measured by ASCA in this X-ray band, there were clear issues with the emission from highly charged iron ions, in particular in this band around 10 angstroms and then around 15 angstroms. This was again, this was a mystery taken from the data, and one of the first successes of the work on EBIT and this collaboration were measurements that very quickly were able to explain the deficit in the models near 10 angstroms. So basically, measurements in EBIT were able to identify a series of lines that had been missing from the models that were applied to interpret the ASCA data. These are basically Rydberg lines. These were lines from high-lying atomic states that were simply not included. They were evident in the EBIT data and were sufficient to explain the bad fit and explain the data from ASCA. Now, the explanation of the poor fit near 15 angstroms, however, remained unexplained, and has been the subject of quite a bit of work over the years. It was narrowed down to an issue with the ratio between 2p transitions in the n equal 2 shell between from the n equal 2 to n equal 3 shell between the 2p and 3d transitions in neon-like iron 17. So this is iron stripped down to 10 electrons. And there are two resonance lines in this system, in this transition, and their intensities were not matching what was measured in the ASCA data. And again, this has been this has turned into a long-standing problem. The laboratory measurements on EBIT were successful in making a very good measurement of what the intensities should be, or what the ratio of these two lines should be. They were also successful in explaining why the ratio, as it turned out, varied in the sun, and that turned out to be because there was blending in these lines from iron 16, so the next door neighbor ion. So again, this was a success of the program, but you can see that from that panel labeled line ratios that the laboratory measurement there disagreed strongly with all of the theoretical calculations that had been done, and continued to be done over the years. In fact, oddly enough, my experience, when you do an experiment, all the theories tend to converge on it for some reason. Oddly enough, in this case, it seems to have been a repeller effect. But anyway, this is kind of where things have stood. Now, meanwhile, while this terrific work was going on the EBIT, the laser experiment, the ability to measure photoabsorption in laser-produced plasmas was becoming much improved. So techniques were being developed here, suggested by Steve originally, that I think were not yet ready because of the state of the lasers, actually, and the fact that they were not capable of producing reproducible targets, and in fact the techniques were not available to fully characterize the systems that were created. A lot of work got done on this, and I think it's, let's see, as you see over sort of the decade of the 90s, there was tremendous success in pushing this along and making some interesting and consequential measurements of photoabsorption and photoionization, basically of X-ray opacity, using laboratory laser-produced sources. You see there's a series of, this was done by a number of people, including Paul Springer and Ted Perry at Livermore. You know, some of the advances here were actually combining different laser beams, measuring different things at the same time, as well as impurities into the target that allowed you to constrain both the density of the plasma you were making, for example, here through just basically X-ray radiography, and also the temperature of the plasma you were making through basically K-shell spectroscopy, something which in principle is easier to do than the opacity measurements being made. So these challenges were being met, and actually, I think it really had some major consequences in astrophysics. The first, or one of the most significant ones certainly, was the role of these laser-produced plasma experiments in validating astrophysical opacity models, invalidating several astrophysical opacity models, and then validating a set from a simulation code called OPAL, which was developed at the laboratory. So here, for example, on the lab's laser at the time, the 30 kilojoule NOVA laser, measurements of iron targets, the opacity of iron, or the photoabsorption in iron, were compared with OPAL models at temperatures of 20 volts and densities of 10 to the minus 2 grams per cc. And you can see the comparisons there, which both validated what was in the models, and also did a fairly good job of validating the predictions of the models in terms of the Rosalind mean opacity, which is one of the measures of opacity that goes into radiation transport calculations. Actually, so some very nice experiments were done at the laser, and also at the Z facility, a Z-pinch facility at the Sandia laboratory, where considerably lower density plasmas were created and measured. And of course, astrophysical plasmas tend to be lower density than what we can make in the laboratory, so getting to lower densities is actually a good thing and allows us to do a better job of connecting laboratory measurements to what's relevant in astrophysics. So these were very nice experiments, and in fact, again, they had a big impact because before these opal opacities existed, and were in fact validated through these experiments in the laboratory, stellar models notoriously failed in predicting the periodicity of a class of stars called Cepheid Variables, which are among the standard candles which exist for dating the universe. The stellar models that existed up until this time were just complete failures at matching the mass and frequency characteristics of these systems, and so didn't allow us to do a good job of using them as systems. The opacities also turned out to be, the opacities from OPAL also turned out to resolve problems of helioseismology, lithium depletion in the Hyades cluster, and pulsations in Beta Cepheid. And by the way, keep this in mind, so I'll come back to this. This seemed to be a real capstone, actually, on this issue of astrophysical stellar opacities, but I'm going to come back to this at the end of the talk, so keep it in mind. The experiment that I showed at the very beginning that Steve tried to do was actually to try to look at X-ray transport, photo absorption in something mimicking an X-ray photoionized nebula. And like I say, that at the time, I think it kind of ran aground on a number of problems in terms of characterization and the uniformity of the plasma, all these issues. But in a series of experiments and publications by Bob Heater, Mark Ford, and Steve Rose, actually demonstrated the ability to make these plasmas, characterize them, characterize their uniformity, put them in steady state, and do photo absorption measurements on them, and that's shown here. This actually was done. Whoops. This was done again at the Z Accelerator at Sandia, and led to I think I got it, and led to what I think is probably the first set and only set of benchmark data on the models for X-ray photoionized nebula. Basically, what was done here was the ionization balance, the distribution of charge states in the plasma under known conditions was measured through photoabsorption measurements, and compared to the models that were supposed to simulate the data that was obtained from these from X-ray photoionized nebula. Now, so let's see, this sort of runs us up through 2004 or so, and for some reason, either because I wasn't paying attention or because I ran out of steam looking things up, I'm not sure, it seems like nothing happened until about 2012 or 2014. I think it may also have to do with the fact that the next big development in laboratory sources, it turns out, came online in about 2012, and that was the National Ignition Facility at Livermore, which is a 2 megajoule laser with actually profound capabilities and precision and reproducibility, addressing some of the issues Steve, I think, turned up 25 years before, and that were worked on very hard in the meantime. So this is just sort of a cartoon of what we were imagining that we could do with NIF in terms of studying high energy density conditions and in particular high energy density astrophysics. In a situation where NIF actually ignites a fusion reaction, the instantaneous neutron fluxes are equivalent to those out of a supernova. Even if you don't ignite a fusion reaction, they're pretty darn big. Sorry. The power of the laser actually allows you to reproduce thermal plasmas in the conditions of stellar interiors up till this time, actually. Generally, it was atmospheres that could be explored. The laser had enough power to drive samples to pressures 50 megabars and beyond. In fact, pressures that were equivalent to those that were expected or should be found in the center of giant planets. And back to that X-ray photoionized nebula, in fact, produce X-ray fluxes equivalent to what you would find in X-ray photoionized nebula. So I'm going to go through some of the, over the last couple of years, just over the last couple of years, some of the very nice results that have come out, I think, in using NIF, and I have to say, other large lasers. So the other, its companion laser, in a sense, is at University of Rochester, the Omega laser, and a great deal of work, preparatory work for NIF went on there, and actually is continuing to produce very interesting results. So one of the, I think one of the most profound things that's come out of NIF has been a platform that allows us to ramp solids in compression up to, as I said, 50 megabars and beyond planetary core pressures. And this is just as recently as, this was summer 2014, reported in Nature. Actually on the cover of Nature was a report of actually doing this in diamond. Basically creating conditions in the diamond sample equivalent to those in giant planets. And one thing I want to note here is this was done actually in a collaboration with scientists from UC Berkeley and from Princeton, and is just one of a series of experiments that are going on at the facility. The facility is actually built for the stockpile stewardship program, but this is one of a number of experiments going on that are pursuing fundamental science and is actually opened by competition to the academic community. So I'll add one thing to here. I don't know if there's a lot of interest here, but it's actually very interesting to me. And this is the first announcement of this. This high pressure capability was actually developed because in the end what we want to do is study plutonium at very high pressures. And this ends up being techniques that can be directly applied to that. And in fact, the first plutonium shot was fired on NIF last night at 8 p.m. Actually, it looks like excellent data was obtained. But more importantly than that, we got it off before we got a court injunction telling us we couldn't do it. So this is just actually, so this is just came out this month. Again, in this case, shock measurement, so using NIF to drive shocks into silica and other SiO2 materials. Stishovite, silica, equations of state, so conductivity, equation of state, and melt curves have been measured at high pressures in these systems, and actually discovering, I think, newly discovering that liquid silica is conductive at high pressures, or is liquid and conductive at high pressures, with hints that if you in super Earth exoplanets where these conditions are met, there could be contributions from an ocean of liquid silica, basically, to magnetic field generation in these systems. Now, this is just to step beyond astrophysics and things astrophysical for a second. The ability to compress a solid up to 50 megabars, actually, when you sit down and think about it, is kind of exciting. In fact, it's a little hard to tell exactly what it means. Usually when you think of something going up to that high a pressure, and by the way, for those of you who are actually high pressure scientists and use pascals, I apologize for using megabars. If you are a high pressure scientist, you can make the conversion in your head. I can't. But in fact, as you go to higher and higher pressures in a solid, again, without melting it, and that's the trick, and that's the unique thing that NIF may enable us to do, or in fact enables us to do. You start to get into a complex regime where the pressure you're exerting is equivalent to atomic pressures, or pressures within the atom, and you start to normal solid state physics doesn't apply anymore. Atomic orbitals start to overlap and interact strongly between atoms. And the expectation here is that there may be entirely new physics to be seen at these very extreme conditions. Now, there are to talk about some of the other very interesting things going on in laboratory astrophysics, in particular enabled by these large lasers, NIF, Omega. Nuclear physics is a bit of a surprise. So this has been proposed, this was been looked at for about 10 years now, and the question has been whether you can actually make nuclear physics measurements in the plasmas that are produced by these large lasers. And there's tremendous skepticism associated with this, not least of all from me, because as Steve found originally, these are tremendously dirty systems. And even if you can make them well characterized and uniform, the idea that you could make a measurement with the precision you could imagine on it with the standard accelerator measurements of nuclear physics quantities is really, I thought was a bit of a stretch. But if you could, there are some very interesting things about these systems. One is, as I mentioned, the neutron brightnesses can be tremendously high. And that means that you can start to look at, for example, kinetics, multi-step kinetics, for example, or multi-neutron processes in nuclei. There's also, of course, the fact that plasma is there. Here it's just interesting to observe that most of the nuclear physics that's been done and applied to astrophysical systems, in particular plasma astrophysical systems, didn't have a plasma in them. So any coupling that might exist, any influence that might exist between the plasma and the nuclear science was either theoretical or was extrapolated or was simply missing. And so the opportunity exists here, again, if you could make precision measurements to actually start to disentangle or look at the effects of the plasma on the nuclear physics. I think this is really the first demonstration that this was actually possible. In 2011, this was done at Omega by Johann Frenzy and a group and a collaboration, including Rochester, the Omega laser there, and Lawrence Livermore, doing really very high precision measurements of neutron deuterium and neutron tritium cross sections. And you can see the comparisons with theory there. This, I think, was one of the things that I think was decisive in convincing people that it was actually a chance of being able to make interesting and meaningful and precision measurements using these systems. This is now just recently, this is August 2013, a measurement of the triton-on-triton neutron spectrum using the NIF. Again, very high precision. In fact, the error bars are in the paper are reported as being the size of the circles in that plot. In fact, leading to the first instance of unambiguously disentangling the 5 helium intermediate, the 5 helium ground state, intermediate state, and triton-triton scattering, shown as that peak at just above 8 MeV. Again, these scattering experiments, basically fusion reactions, continue to be studied. This is now work back at Omega. This is work being led by Alex Zylstra, I think is a graduate student at Omega, who's looking at 3 helium, tritium, 3 helium, and proton-deuteron reactions, all of which are relevant to Big Bang nucleosynthesis. At the Omega laser, and you can see there the measurements in the blue curve, and our matrix fits in red. The goal here is to improve the R matrix calculations of these cross sections, and you can also see that there are some very interesting physics that come out in these measurements. And the one interesting to me there is the 5-lithium resonance that clearly comes out in the measurements. And by the way, these are low energy measurements that actually can't be made, I believe, at accelerators, and could only be done using these systems. Now I'm going to turn to what has been a hope for a long time, which is that you could use these lasers to do some actual real exotic plasma physics relevant in astrophysics. And I think some of this actually has been motivated and by Roger here. And again, this success in this has awaited these very powerful lasers. And the results that I'm showing are actually very, very new. So this is in 2012. This is Nathan Kuglin led this work. He was a postdoc at the time. He's now at Rochester, now at Livermore Lab. And in these experiments, two plasmas are created and streamed at each other with high velocity. And the idea is to try to mock up the kind of collisionless systems that are expected to exist in the universe and lead to strong magnetic fields through the mediating effect of shocks being created in these collisional systems. And one of the real mysteries in all this was how a collisionless interaction could lead to a shock, and it's the magnetic field mediation that's expected or has been theorized to be what leads to this. But it's never been seen. It hadn't been seen in the laboratory. The hope was to actually see it there. This is the first indication in this experiment that was actually happening. Creating these counter-streaming plasmas and actually looking at their electromagnetic structure of the collision using protons. This is basically proton radiography and looking at these protons being bent by the electromagnetic fields formed at the intersection of the beams. Actually, large-scale structures were observed. Not necessarily explained, but they were observed and with the hope that they could shed light on this connection between collisional shocks and strong magnetic fields. So this is, again, 2015, just this month, in Nature Physics, an improvement on those experiments where the observations here show a clear evidence of a connection between the creation of the magnetic fields and what was a prediction was that the Weibel instability would produce these strong magnetic fields. The signature of the Weibel instability in this case is sort of a striation in the field structure, and that's clearly evident in the data that's shown there on the left-hand side. Again, taken by proton radiography here with much higher, it turns out, resolution. In fact, these are fusion neutrons, fusion protons that are being used at a single energy as opposed to what was used in the previous experiment. And this approach continues to be improved on, and at NIF there are experiments underway now to try to do a better job of actually diagnosing this Weibel-mediated collisional shocks, actually trying to measure the spatial and temporal structure of the shock itself using the multiple diagnostics, Thomson scattering diagnostics, and backscattering diagnostics that are available at NIF, and these are experiments that are actually ongoing as we speak. So I'm going to wrap up and just, I want to come back. I'm going to skip this here and just come back to this opacity subject that I thought, and I might have conveyed was actually the end of the story. Those opacities I told you about seem to explain everything from pulsating stars to Campbell's soup or something. But in fact, as sometimes happens over the years that have passed since then, the helioseismology measurements, in particular, the solar helioseismology measurements improved or changed, or well, improved markedly, and the models based on those opacities that were used no longer fit that the measured helioseismology. And the reason is because the metallicity, the amount of iron and other metals that are now understood from those measurements to be in the abundances that are expected in stars have gone down, which means that the opacity is too small that we were using before. So this has been looked at by a group at Sandia on the Z machine. Jim Bailey leading this. Jim's been working on opacity measurements on this machine for a long, long time. And again, this is just, I think this month, this just came out in some very, very careful measurements that we haven't been able to find anything wrong with yet, although we've looked very, very hard. They seem to measure an opacity that's about, for iron, under stellar core conditions. Remember, we couldn't do stellar core conditions before. That's twice as high as what's predicted, as what the models predict. And this would actually take care of a fair part of the discrepancy that exists now. So this is very tantalizing, very interesting. I actually have someone at the lab who's writing a paper right now who believes that if these measurements are correct, it violates the oscillator strength sum rule, which is a sort of a fundamental unitarity-based statement that all of the oscillator strengths out of a given state have to sum to 1 or something like that. It looks like this measurement may violate it, which either means they may have done something wrong, or there's something fundamentally wrong with our quantum mechanics. So I'll let you choose which one to believe. I want to now come back to EBIT and this mystery of the 2p to 3d transitions in the iron 17 system. And I told you that sort of is a problem that's languished. It was worked on. It couldn't be. It turns out the way to make progress on it and make a definite statement about it was to combine EBIT with LCLS. The last connection between Livermore and Slack here. So sure enough, Peter put an EBIT on a truck and dragged it out here. He has a picture of the truck. I don't have it in here. And actually fielded the EBIT, the electron beam ion trap, in the soft X-ray hutch of LCLS. There it is. And did a series of measurements, again, with Steve as a collaborator, that because of the ability to excite these systems purely with the photons from LCLS and not mediated through collisions in the plasma, gave a very clean measurement of the oscillator strengths for these transitions, which allowed a very nice comparison between the oscillator strengths and theoretical predictions. And what you can see there is that they don't agree whatsoever. So there's a fundamental problem with the predictions, the theory that's being done for these multi-atom systems, just in calculating the oscillator strengths. They don't agree at all with the measurements. It almost certainly has to do with multi-configuration effects, the fact that there is mixing between the zeroth order basis sets basically for these multi-electron systems that's not being handled correctly. But we don't even see any convergence here when you add the extra states in. So this, again, very new questions out of answering an old question. And I'm going to stop there, and I'm sorry if I've gone a little bit over.
Thank you very much, Bill. Are there questions? One or two before lunch? Fiona.
So I had a question. Can you explain how you measure the magnetic field in that Weibel instability measurement?
Not in detail, but the measurement is done using a beam of protons. So it's basically measuring the deflection of the protons and working that back to a measurement of the. So measuring the deflection as a function of space and time on an image plane, and working that backwards to a intensity, a magnitude, and temporal and spatial structure for the magnetic fields. It's actually a fairly well-developed technique, but I can't go into. I can't really explain it better than that.
Others? Okay, well, let's thank both Bill and Jason. And I'm told lunch is where it was yesterday, and we'll be back here at 1:30.